Here comes our last video for chapter 19 and also our last video before the next test and the 25th QOD video of the year so far. So we've been talking so far in chapter 19 about spontaneity, and we've really been talking about spontaneity in terms of the entropy change of the universe. That is the sum of the entropy changes in the system and the surroundings. Um, it would be useful, actually, although we can use that as a way of determining whether a reaction is going to be spontaneous, it would really be more useful to us in terms of talking about chemical reactions, um, to have another indicator of spontaneity that would do a couple things for us. Number one, that would be expressed in terms of energy rather than entropy changes, because energy changes are relatively straightforward to calculate and tabulate. And then that it's expressed only in terms of the system rather than trying to think about entropy changes of the system and the surroundings. If we had something that was in energy terms and was only expressed in terms of the energy of the system. So we have that in what's called free energy. And so let me talk about how you can derive the equation for determining what the free energy of a system is. By the way, the concept of free energy was first put forward by an American chemist in the 19th century named Josiah Gibbs. And it's actually defined as the maximum amount of useful work that could be gotten out of a chemical reaction. Um, and so it's called delta G in honor of Gibbs, and it's also referred to often as the Gibbs free energy, not just free energy. Um, Although you'll hear it described in both ways. First of all, we can get to this idea of an energy based indicator of spontaneity this way. Let's go back to this equation that says that the entropy of the universe, the change in entropy of the universe, is going to be equal to the change in entropy of the surroundings plus the change in entropy of the system. And recall that if that delta S of the universe is positive, we have a spontaneous process. If it's negative, we have a non-spontaneous process. Well, I can also recall from previous conversation that the delta S of the surroundings is equal to negative delta H of the system over T, in which T is the temperature at which the process or reaction is occurring. And so recall that if delta H is negative, if delta H is if we have an exothermic reaction, delta H is going to be negative, and negative negative is a positive, and the entropy of the surroundings is going up. And that makes sense because an exothermic reaction is heating up the surroundings and increasing the entropy of the surroundings. Okay, well, we can substitute this equation into this equation, and that gives us the entropy change of the universe is the negative enthalpy change of the system divided by temperature plus the entropy change of the system. And so what that has allowed us to do now is to get the whole right side of this equation in terms of changes in the system and not in terms of changes in the surroundings. Okay, we're going to continue with that equation that I just had on the previous slide. The entropy change of the universe is equal to the negative enthalpy change of the system divided by T plus the entropy change of the system. Now, the next thing I'm going to do is just an algebraic operation, which is to multiply both sides of this equation by negative T. And when I do that, I get negative T delta S of the universe is equal to delta H of the system minus T delta S of the system. And so now I've got everything here actually in terms of energy, because since the units of entropy are joules per Kelvin, and if I have T delta S, I am multiplying entropy by temperature. So joules per Kelvin multiplied by kelvins is going to give me joules. And so T delta S is an energy term. So this negative T delta S of the universe is an energy term, and the negative T delta S of the system is an energy term. Okay, so now we're going to pick up with that equation, and we're simply going to define negative T delta S of the universe as the Gibbs free energy, which we symbolize as delta G of the system. And so therefore, delta G of the system is equal to delta H of the system minus T delta S of the system. And if we think in terms of what does that mean for sign and spontaneity, when delta S of the universe is positive, then delta G is going to be negative because delta G is equal to negative T delta S. And so when delta S of the universe is positive, that's a spontaneous process. And therefore, a process is going to be spontaneous when delta G is negative, because when delta G is negative, that means delta S of the universe is positive. And when delta S of the universe is positive, that's a spontaneous process. And we have tabulated values for delta for standard free energies of formation are tabulated in Appendix C. Okay, so this is just related to, this is actually something that's a little bit related to equilibrium, which again, we're not going to talk about until the second semester. But we can simply just say this. If delta G is negative, then the reaction is spontaneous as written. That is, it's spontaneous in the forward reaction. If delta G is positive, then the reaction is going to be spontaneous in the reverse direction. That is, it's not going to be spontaneous as written. It would be spontaneous if we turned it around. And then if delta G is equal to 0, then the system is at equilibrium. Delta G being equal to 0 is another way of saying that the delta S of the universe is equal to 0, and that's an equilibrium situation. But again, we're not really talking much about equilibrium right now. Okay, because we have tabulated delta G standard free energies of formation in Appendix C, we can calculate the delta G of the reaction in the same way that we would calculate delta H or delta S from tabulated data. It's simply equal to the sum of the standard free energies of formation of the products multiplied by their coefficients minus the sum of the standard free energies of formation of the reactants multiplied by their coefficients. So here's a typical problem that you could get. This is something I took out of the test bank again. Here is just an abbreviated chopped down version of standard enthalpy of formation, standard free energy of formation, and standard entropy of formation for O2, and then elemental sulfur and sulfur trioxide. And so it asks the question, what is the value of delta G at 25 degrees Celsius, which is at standard conditions for this reaction? 2S plus 3O2 gives 2SO3. Well, to answer that question, we're simply going to say, using the sigma equation that was on the previous slide, that the delta G of the reaction is the sum of the free energies of formation of the products, which in this case would be 2 times the free energy of formation of sulfur trioxide, minus the sum of the free energies of formation of the reactants, which would be 2 times sulfur plus 3 times oxygen. Well, like standard enthalpies of formation, standard free energies of formation are just arbitrarily defined as being equal to 0 for elements in their standard state. And so that makes this very easy because only one of these actually has a value, which is the standard free energy of formation of sulfur trioxide, which is negative 370.4. For oxygen and for sulfur, it's 0. And so this is a very simple equation. It's just 2 times negative 370.4, which is negative 740.8 kilojoules per mole. And therefore, the answer is going to be D, negative 740.8 kilojoules per mole. Now, there's something really, really important to understand about delta G for a reaction, and that is the values of delta G are very sensitive to temperature. And so we could do this reaction, we could do this calculation in this way, just taking the delta G values out of the table, because it was asking us for the value of delta G at 25 degrees Celsius. And so these tabulated values of delta G work well at 25 degrees Celsius, but delta G varies quite a bit with temperature. And you can think about this in terms of the conversation we had previously about the fact that some processes, their spontaneity is temperature dependent. And we talked about the freezing of water being an example, that it was spontaneous below 273 kelvins, but that it was non-spontaneous above 273 kelvins. So if the entropy of the universe, if the entropy change of the universe can be strongly affected by temperature, and delta G of the system is related to the entropy change of the universe by temperature, then it stands to reason that the delta G of the system is also going to be quite subject to temperature. And so at temperatures other than 25 degrees Celsius, we can't just sum up the tabulated delta Gs of the products and subtract out the tabulated delta Gs of the reactants. We have to use this equation and sum up the delta H's of all of the reaction, and then work out delta S of the reaction, and then plug both of those values into this equation to get delta G of the reaction. So I've just said that delta G varies quite a bit with temperature. As it turns out, delta H values are fairly stable with temperature as long as you're not going through it, as long as you're staying in the same physical state. And similarly, delta S values are fairly stable with temperature as long as you're staying in the same physical state. So we can use tabulated values for delta H and delta S across a range of temperatures, but we cannot use tabulated values for delta G across a range of temperatures. And so how does delta G change with temperature? Well, there are two parts to the free energy equation. Delta H, which is the enthalpy term, and the negative T delta S, which is the entropy term. And it's the entropy, it's the T delta S term that is temperature dependent. And so we can construct a little table like this, similar to what we did for trying to determine spontaneity based on the entropy change of the system and the entropy change of the surroundings, and simply now talk about it in terms of the enthalpy change of the system and the entropy change of the system. So if you have a system for which delta H is negative, that is, it's an exothermic reaction, and delta S is positive, that is, the entropy of the system is going up, then that's always going to be spontaneous, because temperature is always a positive value. Therefore, in this case, T delta S is going to be a positive value. A negative value for delta H minus a positive value for T delta S will give you a negative value for delta G, and therefore a spontaneous reaction. Conversely, if we have a reaction for which that is endothermic and the entropy of the system is going down, that is never going to be spontaneous. Remember, if it's endothermic, we're decreasing the entropy of the surrounding. And here we're decreasing the entropy of the system, and so the entropy of the universe must be going down, which would make that non-spontaneous. If they are both negative, that is, delta H is negative, it's exothermic, which tends to be good for spontaneity, but delta S is negative, which tends to be bad for spontaneity, then it's going to tend to be spontaneous at relatively low temperatures, because relatively low temperatures are going to minimize this bad entropy value. Relatively high temperatures are going to maximize this unfavorable entropy value. And the flip side is, what if delta H is positive and delta S is positive? Well, delta H being positive is bad for spontaneity, but delta S being positive is good for spontaneity. And therefore, at relatively high temperatures, this positive value of delta S will be maximized. And at relatively low temperatures, this positive value of delta S will be minimized, and it'll tend to be non-spontaneous. If we were actually going to calculate this, we would do it in this way. We go back, and I've just invented a term called transition temperature. And what I mean by transition temperature, and this is not a technical term and it's not in your textbook, but what I mean by it is the temperature at which a reaction goes from being non-spontaneous to being spontaneous, or the other way around, the temperature at which a reaction goes from being spontaneous to being non-spontaneous. And we can calculate it in this way. We recall that delta G is equal to delta H minus T delta S. Well, what is the value going to be at that temperature at which it changes from being spontaneous to being non-spontaneous or vice versa? Well, that's the temperature at which it is going from negative to positive or positive to negative, and therefore at that temperature, delta G is going to be equal to 0. So therefore we can set delta H minus T delta S. So at the transition temperature, delta H minus T delta S is equal to 0. Therefore, just using algebra, delta H is equal to T delta S. I just got that from adding T delta S to both sides. Now I divide both sides by delta S, and that transition temperature is going to be equal to delta H divided by delta S. So let's try a problem. Let's consider this reaction. This is the reaction of ammonia gas with hydrogen chloride gas to give solid ammonium chloride. And so given this table of thermodynamic data, which doesn't give us delta G values for these substances, but it gives us delta H and standard enthalpy of formation and standard entropies for all these substances, determine the temperature in degrees Celsius above which the reaction is non-spontaneous. Well, in order to do that, we have to first work out the value of delta H for the reaction, which is going to be the delta H of our product minus the sum of the delta H's of our reactants, which gives us a delta H for the reaction of negative 175.9 kilojoules. Then we work out delta S for the reaction. It's going to be the standard entropy of our product minus the sum of the standard entropies of our two reactants, which gives us a negative 284.6 joules per Kelvin. Now, here's a really important thing to recall. So the temperature is going to be equal to delta H over delta S. But you'll notice, and unfortunately, I see as I'm doing this video now that I didn't put units in here, but S values are given in joules per mole Kelvin, whereas delta H values are given in kilojoules per mole. And so in order to divide delta H by delta S, we either have to convert this from kilojoules to joules, or we have to convert this from joules per Kelvin to kilojoules per Kelvin. I'm going to do the former and convert delta H into joules, which is negative 175,900. I'm dividing that by negative 284.6 joules per Kelvin, and that gives me 618.1 kelvins. 618.1 kelvins minus 273.15 for the conversion to Celsius, and rounding to the nearest whole, rounding that answer up correctly gives me 345 degrees Celsius. And so that is D, 345 degrees Celsius is the correct answer. Okay, well, we will have a QOD for this tomorrow, or we will have a QOD coming up as assigned in the assignment and there should be some suggested end of chapter problems for you to work on to prepare for that.